Hey, welcome to another video. In this video, we're going to start learning about the techniques that we generally use to solve quadratics, and there's 4 of them. In the last video, I introduced that. I said we're going to be talking about 4 techniques coming up. I'm going to teach these to you in the order in which you should look for them. So I'm going to teach you them in the easiest to the, I won't say most difficult, but the ones that involve a little bit more work. I guess that means more difficult. So we're going to talk about the square root method first. Then we'll talk about factoring. Then we'll talk about completing the square, and we'll use that to transition into the quadratic formula. So when we're doing this, remember what we're doing. We're going to all have quadratics, and they're all going to be parabolas, and we're basically looking to see if these are going to cross the x-axis, and if they do, where? And if they don't, do they bounce, do they touch, or do they completely miss it and have imaginary numbers? So that's what we're discussing. We're going to talk about the square root method first, why it works so nicely, why it's the first one that you check. So what the square root method asks is, can I find the x-intercepts, or the zeros or the roots of my quadratic by taking a square root on both sides? So the square root method does basically 2 things. It sets the function equal to 0, and it says, can I isolate a power 2 without having any x's anywhere else in the function? If I can do that, then we can take a square root of both sides. The biggest thing that I can possibly tell you here is that, number 1, we need to be able, I guess it's 2 biggest things. Number 1, we need to be able to identify when we can do the square root method and when we can't. Number 2, and I swear this is the biggest thing, when you take a square root on your paper, it wasn't there before, and you're the one who put it on there, with very few exceptions, you have to have a plus and minus right in front of that square root. That's important, because what that does, we learned in the last video, is that these are going to generally have 2 solutions. We're even going to see that on that one, that we're only going to get 1 solution out of, but we're going to get the same solution twice. In order to get that, you have to have a plus and minus in front of that square root. I promise you, it's the biggest mistake that I see students make, especially in like an intermediate algebra class. Now I know this is pre-calculus, but the same mistake still happens. So let's dive right into it. Let's see what the square root method is, when it works, and how to do it. So number 1, hey, do we have a parabola? Yeah, and in fact, that's an upward opening parabola. All of these are going to be, it's not a big deal if we don't have upward opening, they work the same way. But what we do every single time we want to find zeros, or solve a quadratic, or find out where it crosses the x-axis, is we set our function equal to 0. So we're going to do that. We're going to say, let's make x squared minus 18 equal to 0. Now, when we go ahead and we solve this, we go, well, how would we do it? That is the kind of the nature of deciding what technique to use. So here's a thought process I really want to build in your head in order to do these the most efficiently way possible. So when we look at this, we go, well, will a square root method, or will a square root work? The answer to that question lies in, can you get something all wrapped up in parentheses, or just an x or something with a power 2 on one side that contains all of your x's and a constant on the other side? If we can do that, taking a square root will work. If not, then we have to have another technique. Typically, we would try factoring second. Then we go probably to the quadratic formula. I'll show you completing the square, but pretty much as a way to get to quadratic formula. So we look at it. I got x squared minus 18 equals 0. Why equals 0? Because I'm trying to figure out where this function has a height of 0, and therefore if or where it crosses the x-axis. That's giving us our zeros. Well, I've done that. Now, the second thing I ask in my head is, can I get a power 2 by itself? I see an x to the power 2. I see that I can isolate this if I add 18 on both sides. That would get everything on one side, having a power 2 all wrapped up in that exponent, and then a constant on the other. This is what we're looking for. We're looking to get some power 2 with all of your x's inside and a constant on the other side. That's important. That's the nature of the square root method. If that works, then you're good to go. Square root method's going to work. You take a square root on both sides. Why? Well, anytime we have a power 2, we know that to undo a power 2, the inverse of that is a square root. We've just got to do it on both sides. And you go, sweet, I'm done. No, this is going to make your teacher cry. This literally made me cry. Not really made me cry, but like my heart breaks a little. Whenever we do this, we need to understand what square roots do. Square roots, when we square a number, it takes negatives and it makes them positive, and it takes positive and it keeps them positive. Because of that, because these power 2s have the ability to take both 3 and -3 and make them both positive 9, or any two numbers that are opposites and make them the same numbers in output, we need to acknowledge that by saying, you know what, whether I have a positive square root of 18 or a negative square root of 18, if I square positive square root of 18, it's going to give me 18. If I square negative square root of 18, it's going to give me 18. Both of those values satisfy this x squared equals 18. I can plug in square root of 18 here. Square root of 18 squared is 18. 18 minus 18 is 0. I can plug in negative square root of 18 here. Now that's kind of weird to think about, but the negative square root of 18 squared, well, squaring a negative gives me a positive. Squaring 18 square root of 18 gives me 18. If I plug in the negative square root of 18 and square it, I'm going to get 18. 18 minus 18 is 0. It says both of these, and there are two, both of those solutions are valid for this. That's why we have to put both a plus and a minus. It gives us the two solutions that we know we're going to get for quadratics. In general, whatever that highest power is, whatever your degree is, that's how many solutions you're in general going to get for a polynomial. Weird. So for here, we know we're going to get two solutions. We have to have the plus and minus to show us that. So what happens? Well, let's see. The square root of x squared gives us x. On the right-hand side, we do need to still know how to simplify some square roots. We need to be able to take this up and, you know what? Square root of 18, I could write that as 9 times 2. I know the square root of 9 gives us 3. The square root of 2 says, I can't, you know what? I can't really simplify that anymore. It's a prime number. I can't make it a power 2 to simplify the power with the root. I know that I would get plus or minus 3 square root 2. Now, for my students, I have them write this out every single time so that they don't think that this is just one solution. What I have them do is, okay, now I need you to write this as x equals 3 square root 2 and another solution, x equals negative 3 square root 2. This is the fundamental idea of the square root method. You're saying, you know what, I still want to find x intercepts. I'm still going to set this equal to 0, but then we look at what the best technique is. Are there other ways to do it? Yeah, there are. Is this the easiest? Probably. For me, it's the easiest. For a lot of students, it's the easiest, especially when we start getting into some of these things. The square root method is extremely nice when we can use it. Again, the fundamental idea for having the square root method is, can I get a power 2 on one side that contains all of my x's, like this, x squared, and a constant on the other side? If I can do that, take a square root on both sides, put a plus and minus around your constant. So square root of your constant, put a plus and minus there. You don't need it on both sides because it's redundant if we do it. We don't need that. So take a square root on both sides and put a plus and minus in front of your square root of your constant, simplify your square root, and then you're going to have most of the time you're going to have two solutions. Well, let's look at that. What are those solutions? This should tell you something. Does this say that we cross the x-axis twice? Does it say that we bounce off the x-axis once? Does it say that we miss the x-axis? And here's how to determine that. In the last video, we talked about the only 3 cases we can have, where we cross, we bounce, the vertex bounces or touches the x-axis, or we completely miss it. How to determine that? If you have 2 distinct solutions, like these are different numbers here. They are numbers. You can plug them into your calculator. It's going to give you some sort of a decimal on your x-axis where this parabola actually crosses. So if you have 2 distinct numbers, usually well, I can't say usually a positive and negative. They can both be positive, both be negative, but 2 distinct numbers that do not have i's in them, then you are going to cross the x-axis twice. This is giving you 2 zeros or 2 real x-intercepts. That's what this is talking about. If we get 1 real solution, so no i's, but you get basically the same number twice, they're not distinct, that means that you're bouncing the vertex right off the x-axis. And if you get i's anywhere in these problems, any sort of an imaginary number, any sort of a complex number, that means that you're missing the x-axis. So right here, we look at this, we go, all right, hey, I'm going to solve for 0, set this equals 0. I'm going to find my x-intercepts. I'm doing that. I'm saying the square root method works great because I can isolate a power 2 with all my x's and a constant on the other side. I'm taking square root. I'm acknowledging I must have a plus and minus. It's a big deal. And then I'm simplifying as much as possible and then saying, yes, These are two numbers, they're different numbers, and they don't have eyes in them. That means that we have two real zeros, two x-intercepts. Let's do a few more. We're going to run through these fairly quickly. The ideas that I'm looking for are that you understand, number one, that we're setting a function equal to 0 to find x-intercepts. Number two, whether we use this technique or any other technique for solving quadratics, we're getting the same thing. We're finding those zeros. Number three, when you set this equal to 0, you need to understand when the square root method works and then how to do it. So when it works is when I can get a power 2 by itself, constant on the other side. How it works is you're taking a square root of both sides and you're putting a plus and minus in front of the square root of your constant. So let's set this equal to 0. And we're saying, all right, that's going to let us find any x-intercepts by setting the height of the function equal to 0. Now we think, can I get this power 2 by itself on one side and a constant on the other side? If I can do that, so without any other x's floating around, if I can do that, well, then I can take a square root of both sides. But what isolated means is that there's no addition buddies, no multiplication buddies, nothing, just something to a second power. So when we solve this, we go, all right, let's add 33. I'm noticing that I just have an x squared. I'm going to be able to get that by itself, but man, you really have to get it by itself. This is not good enough. I see a lot of students go, oh, I understand this. Yeah, I can take a square root. I'm going to get it here and then take a square root. Please don't do that. It's making a tremendous amount of work and it's not right. Because if we take a square root around 3x squared, the square root of 3 is very hard to deal with. So instead of doing that, what we're going to do, we're going to divide by 3. We're going to get that second power, the something to the second power, the x to the second power or parentheses to the second power, get that isolated. So let's divide by 3. So dividing both sides by 3, we get this x squared equals 11. This is what we mean by isolating a power 2. We mean that I have all of my x's inside something being squared. Yeah, there's only one x, so that is isolating a power 2, and I have a constant on the other side, no other x's anywhere to be found. This is perfect. This says our square root method is going to work. So when we do that, we take a square root of both sides and we think, you know what? In taking a square root and solving for x, we're understanding that a power 2 takes both a positive and a negative solution and makes them positive. So in understanding that, we're saying, you know what, the square root of 11 is a solution here, but the negative square root of 11 is also a solution. Because if I take the square root of 11 and square it, it would give me 11. So take it here and say, hey, square root of 11 squared is 11. Or the negative square root of 11 squared, it's also 11. So to understand that, that means that we're understanding why we're putting the plus and minus. All right, I'm going to put this here because both the positive and negative version, the opposites of this solution, well, they would both satisfy this equation. So power 2 and a square root, those are inverses. On the right-hand side, we can't simplify the square root of 11. There's nothing to do with this, but we are going to write it as the positive square root of 11 and the negative square root of 11. And now I want you to think in your head, are these two real x-intercepts? Are we going to cross the x-axis twice? Are we going to bounce off the x-axis with a vertex? Or are we missing it? Well, are there any eyes? No. Are these unique? Yes. So they're not the same answer twice. This means that this parabola, which is upward opening, positive, is going to cross the x-axis 2 times at exactly the square root of 11 and the negative square root of 11. These are called exact solutions. So when you don't approximate, you don't plug in the square root of 11 on your calculator and find a decimal, that's what they mean by give me an exact solution. This is exact. Now, exact to us sometimes doesn't make sense. He's like, well, I don't know what that is exactly. No one does. No one does, because you don't know what the square root of 11 is forever, because it goes forever without repeating. It's not a fraction. It's not rational. So when we say exact, we wrap it up in a form that contains all the information, like the square root of 11. It says, okay, this is what the number is. An approximation would be where you put in your calculator and you go, okay, this is like 3 point something. That's an approximation. So when they ask you for approximation, yeah, put it in your calculator. If not, these are exact solutions, and this is exactly where this parabola that's upward opening would cross 2 times the x-axis. That's what we're doing. Okay, moving on. We have 4 more to do. These 2 are special cases that I need to show you. So really there's just these 2 that I need to make sure that you completely understand, and then we're practically done. We'll talk about those ones. They're kind of neat. I want to show you the other cases because these are all real solution up to this point. So we have a function g of x equals x plus 2 squared minus 1. You know what? One of the first things that people really want to do here is distribute. They go, yeah, let's FOIL that all out, or whatever you want to do. That might not be the best thing. When we go through solving quadratics, the first thing I need you to understand is that solving means setting equal to 0 to find x intercepts roots or zeros. So solving says, I'm going to take my function, I'm going to say, find me the x value or values where my height is 0. This is inherently finding out where we cross the x-axis. Now, categorize this. Can you, and go through the steps, can you solve this by using the square root method? If the answer is yes, then you should do it. If the answer is no, then we try to factor. If you can't do that, then we try to do quadratic formula, which always works, but it's a little bit more tedious. So we think, can we do the easiest things first? That's why there's 4 techniques, because some are easier, but don't work all the time. Some work all the time, but they're more tedious. So we look at this and go, all right, I'm finding out where the height is 0. I'm finding out where this crosses the x-axis, bounces, or if it misses. How to solve this? Well, we're thinking about it going, can I isolate a power 2 so that all my x's are within that power 2? Just like here, can I isolate this so that all my x's are within the power 2 and have a constant without x's on the other side? Yes, yeah, I can. If I add 1 to both sides, x plus 2 squared equals 1. This is isolated a power 2 that contains all of my x's. There's no other x's being added, subtracted, multiplied, divided. No x's over here next to that constant, which is why it's a constant. This is when the square root method shines, because it's a 2-step, like a 3-step process. We do this and we go, all right, now that I've isolated the power 2, know that x is floating around, I can take a square root, because I know what we can do basically whatever we want in equations, as long as we do it to both sides. So we say, how do I undo a power 2? Take a square root. Just do it to both sides, and recognize that any time you put a square root on your paper, you have to do a plus or minus in front of the square root of your constant. This is saying that when I plug this number in, I would get a positive and I would get a negative. But squaring that is going to give me that positive 1 no matter what. So this is why we do that. On the left-hand side, hey, the square root of a square, those are inverses. You basically just compose them, and it cancels out. So it's x plus 2 equals plus or minus the square root of 1. Simplify the square roots. So the square root of 1 is 1. So we'd have plus or minus 1. This gets a little confusing for students. How in the world do you solve this? We're going to solve for x, and we're going to solve for x by subtracting 2, but it's important where we subtract that 2. Where we subtract the 2 should not be like this. We shouldn't subtract 2 here and subtract 2 from the 1. Why? Well, because that stands for 2 different numbers. That stands for positive 1 and negative 1. And if I subtract 2 from it, one of those would be right and one of them would be wrong. So here's what I would like you to do. This kind of trains you a little bit for the next few problems. Instead of writing this out as, which you could do, this is perfectly acceptable. Instead of writing this out as x plus 2 equals positive 1 and x plus 2 equals negative 1, you can certainly do that. You can solve each one independently and it will give you the correct solution. That's a fine way to do it. What I'm going to try to get you to do is to do this. Say, all right, if I subtract 2, maybe I put it in front of that plus and minus. So I would get x equals negative 2 plus or minus 1. And the reason why is because that looks a little bit more like what we're going to get on quadratic formula. That looks a little bit more like what we're going to get when we complete the square. It's going to kind of flow through this. And it looks a little bit more like what we're going to get right here. So the reason why is so that you can start to train your mind that this is 2 solutions. How do we get both solutions? Well, if we go and take our constant negative 2 and we add 1, so kind of the high road, negative 2 plus 1, and then take the low road, negative 2 minus 1. That's going to yield both of those solutions for us. So let's look at it. Man, now we're kind of understanding this. This is negative 1 and this is negative 3. So negative 2 plus 1 is negative 1. Negative 2 minus 1 is negative 3. In your head right now, you should be thinking, this is a parabola. Sure, it's got a power 2. Is it upward opening? Yeah, in fact, this is a shift. Look at this. This is a shift down 1. Is this making sense? This is a shift left 2. So down 1, left 2. This should be upward opening. It should have 2 x-intercepts. Down 1, left 2. Wait a minute, those x-intercepts are probably negative. Yeah, they are. This is exactly where this parabola crosses the x-axis. How do we know it crosses, doesn't bounce? We know it doesn't bounce because these are different numbers. We know it crosses because they're not imaginary numbers. So this is 2 x-intercepts where this parabola that's upward opening crosses the x-axis. You know what? We can plug it in. We can see they both work. So if we plug in negative 1 plus 2 is 1. 1 squared is 1. 1 minus 1 is 0. Oh yeah, okay, if I plug this in, I get a height of 0. That means it's on the x-axis. Plug in negative 3. Negative 3 plus 2 is negative 1. Wait, that's the same number we just got, but it has an opposite sign. Those are opposites. But negative 1 squared is positive 1, and 1 minus 1 is 0. This is the reason why you must have that plus and minus. That plus and minus gives you the ability to say, okay, one of our solutions is positive, but the square's going to keep it positive. One of our solutions, when we plug in some numbers here, is going to be negative, but the square is going to make it positive. That's why we need that plus and minus to maintain that idea. I hope this is making sense. I hope you're seeing that we have 3 examples where we are actually crossing the x-axis because we don't have imaginary numbers, and we have 2 distinct numbers. Let's try the last one before we get into some special cases. Same thing, I'm going to walk through it fairly quickly. We go, all right, this is a quadratic. How do we know? If you were to distribute it, you'd have an x to the second power. That is a quadratic. I want to find x-intercepts. The first thing we do whenever we want to find x-intercepts is set your function equal to 0, no matter what function you have. And now we categorize it. So we've said quadratic, sure, I'm thinking in my head what I should be getting. I'm thinking I should either cross twice, bounce once, or miss completely. Then I'm saying, how do I find those values? Well, I set it the function equals 0. I've done that. Now in my head, I'm thinking parabola. I'm thinking, okay, now what technique do I use to solve this? Do I jump directly to quadratic formula? No, that's a tremendous amount of work. We'd have to distribute, combine like terms, find A, B, and C, plug it into a formula, and then go through it. That's not super fun. Is there an easier way? Yes. So we start with the easiest way and see if that'll work. The easiest technique we have is a square root method. Can we solve this, or can we isolate, I guess is a better word, a power 2 with a constant on the other side? So something that has all of our x's in it raised to the second power and a constant on the other side. The answer is yeah. This already has a power 2, and that's a constant. There's no other x's that are outside of that parentheses, outside of that thing that's being raised to the second power. That's what we're looking for. Something that contains our x's raised to the second power. So if we have that, we can isolate the power 2, then we do it. One thing I want to mention right now, just glance at it for a second. What if we would have had something like a 4 out here and a 4 out here? Before you take a square root, you would have to divide by 4. Please see that. Please see that when we talk about taking a square root, just like right here, it's why I gave it to you, just like right here, before you take a square root, you actually have to have the thing raised to the second power completely isolated. Nothing around it at all being multiplied, added, or subtracted, or divided. So if we had the 4, we'd say, yeah, I can still isolate the power 2, but it's a 2-step process. Add 32. Here you'd be dividing by 4. You would not take a square root right now. Now, okay, we go, all right, now that we have the square isolated, if we take a square root on both sides and we think every time I take a square root, I'm going to do a plus and minus. Why? Because squares maintain positivity for both negative and positive values. So that's why we're doing that. On the left-hand side, power matches the root. We're going to get 2x plus 3. On the right-hand side, we're going to simplify the square root of 32 as much as possible. 32 is 16 times 2, so we can take the square root of that. Notice how I'm picking the biggest number I can take the square root of, not the smallest. So I'm not thinking 4 and 8, because if I did 4 and 8, I'd have to do this process twice. Once with 32, and then we'd have a square root of 8, we'd have to do it again. So I'm thinking, what's the biggest perfect square that I can simplify out of this? And it'd be 16. Square root of 16 is 4. The square root of 2 is, I don't know, let's leave it. So we have looked at this. We've said, I'm going to set it equal to 0. Then we've categorized it. We've thought, I can isolate the power 2. Oh, the square root method works just fine. I'm going to fully isolate this. If I would have numbers in front, I'd still divide them. Add 32, I'm going to take a square root. I understand that anytime I take a square root, I'm adding that plus and minus there. I'm simplifying the radical that we get. And then we continue to solve for x. And in doing that, we're going to use what I taught you up here. We're going to say, where would I subtract the 3? Well, because I trained you right here, we're not going to try to subtract the 3 from a radical. It doesn't work. This has a square root 2. This doesn't. They're not like radicals that we learned about in like an intermediate algebra class. We can't subtract those things. So where we put the minus 3 is in front of that plus and minus. That's why I showed you this, so that we would understand how to organize our problem here. So when we subtract the 3, we have 2x equals negative 3 plus or minus 4 square root 2. So we're just solving for x. If this had been any other number, we'd be subtracting 3. Do the same thing. Just know where to put it. We put it in front of that plus and minus. Lastly, we know that we've got to divide by 2. We do this for any type of problem solving for x where you have 2x in front of it. We divide by 2. Do the same thing. We can divide the whole entire expression by 2. So our x, dividing both sides by 2, would equal negative 3 plus or minus 4 square root 2, and then all divided by 2. I need to make a couple notes. You should be making a couple notes here. That number 1, things need to be simplified. So that means our square root needs to be simplified. This expression would need to be simplified if possible. I want to, man, you got to pay attention to this. Please don't miss this. There's things you can do and things you can't do when simplifying. What you can't do, don't simplify little pieces of this fraction. You cannot simplify the 4 with the 2. It's impossible. If this had been like a number like 6, you can't simplify just the 6 with the 2. That's impossible. What you can do, if it's possible to factor, or if these have a common factor, of in these two terms, and if that simplifies with a 2, what you can do, bear with me here for a second. If this had been a number like 6, I know it's not, but just bear with me. If that had been a number like 6, this is something you must simplify. So we'd say, how would you do that? There's kind of an easy way that doesn't really show you what's going on. I'm going to talk about that one. It's what most people do. And then I'll talk about why it is that that works. What most people do is they go, all right, divide each of these 3 numbers, not that one, divide each of these 3 numbers by 2. And that actually works. So you go, all right, 6 divided by 2 is 3, 4 divided by 2 is 2, 2 divided by 2 is 1. And you can simplify like that. Why that works is because if you would have something that has a common factor, you could factor it out. So if we factor out the 2 from negative 6 and 4, factoring out the 2, that'd give you, let's see, negative 6 divided by 2 is negative 3. 4 divided by 2 is 2, and we'd have this 2 on the denominator. Then you can simplify that away. That's why it works. It's a factoring idea. We know how to simplify fractions. It's a factoring idea. That works the same if you just divide all 3 of these numbers by the same number. So that does work. Be careful with that. What I see is students make mistakes and they'll just divide 2 numbers. You cannot do that. That's a no-no. The last thing I need to mention to you before we get into our special cases is that I would really like it if you would make sure you understand that these are 2 solutions. So I'm going to have you write it like that. I'm going to have you understand that this means negative 3 plus 4 root 2 over 2. That's one solution. And x equals negative 3 minus 4 root 2 over 2. That's another solution. Why do we have 2 of them? Because we didn't forget our plus and minus. Now, last thing, the very last thing. What do those mean to you? Is that a parabola? Yes. Is this crossing the x-axis twice? Is it bouncing once, or is it completely missing it? Don't let weird-looking answers give you the wrong impression of what's going on. So here's how to think through it. Are those different answers? Yes, so we know that we're not bouncing. Get that. We know we're not bouncing because we didn't get the same answer twice. We have -3 plus and -3 minus, two different numbers. So that means that we have two different solutions. So it's not bouncing. We know we're not in that vertex on the x-axis idea. Do we have any imaginary numbers? Do we have any eyes up here? No. So even though they look weird, these are two real solutions. These are exact solutions, exactly where this parabola will cross the x-axis. These are x-intercepts, the real solutions. They don't have eyes in them, they're not imaginary. There's not just one of them, they didn't happen the same value twice. We have two distinct solutions, and they are exact. They look really weird because we couldn't go right now. Most of us can't go right now. I can't do it and go, oh, that's here on x-axis. I need a calculator. We need to plug this in and do -3 plus 4 square root 2 and then divide that by 2. But think about it. Would it give you a decimal? Would it give you some number with decimals in it that you could go to the x-axis and plot? Yes, because it doesn't have eyes. What that means is that this really is a real solution. This is giving you two spots on the x-axis where this parabola will be crossing it. That's what I need you to know. Now let's move on to the next couple examples. So I told you a couple times that what we're looking for is really three cases: where we cross twice, where we bounce once, and where we completely miss. We've done a lot of cross twice. That happens a lot. This is going to be a bounce. This is going to be we touch it one time, and I'm going to show you why in the form of this, why that happens. And this is going to be we completely miss. So I'm not going to hold you in suspense. That's what's going to happen. Let's see why that happens and why it is that the plus and minus doesn't always yield two distinct solutions. So let's take a look at this. F of x equals x minus 7 squared. Man, is it a parabola? Yeah, and if we distributed that, we would see that that would have an x squared in it. Is it upward opening? Yeah, that's positive. Is it shifted? Yes. In fact, if you really think about this, this is not shifted up or down. This is shifted to the right 7 units, and it's upward opening. Wait, if we had a parabola whose vertex naturally is at 0, 0, and we just shift it to the right 7 units, isn't that vertex still going to be on the x-axis? Yeah. Is it going to cross the x-axis? Is it going to miss it? No, it's sitting on it. It's bouncing off of it. That means you have one real solution. One real, because it does touch it, solution. It's not imaginary. And that's going to bear out in this technique. So let's set this equal to 0. That's how we find x-intercepts for every single quadratic ever. We set it equal to 0, and then we acknowledge what technique is best. We look at this and go, all right, what's the first technique you try? Let's try to do square root method. Square root method says, if I can get everything on one side, all of my x's inside of a power 2, like that, and I can get a constant on the other side, like that, then I can take a square root. So this is isolated already. This is fantastic. And if I take a square root of both sides, I've isolated a power 2 that has all my x's within a power 2, nothing multiplied, nothing added, subtracted, a constant over here, and I take a square root on both sides. And then we know that every time you're the one who takes a square root, you put a plus and minus. On the left-hand side, we get x minus 7. On the right-hand side, we get something that I need you to see. We get plus or minus 0. And I know that's weird. You go, wait a minute, isn't that just 0? Yes. See, 0 is the only number that you can add and subtract from another number and get the same answer. It's this additive identity, right? So you add it and it doesn't change it doesn't change what you get. So this 0 is the only number in the world that we can add and subtract from a different number and get the same number in both cases. So if we do this, it's going to look a little weird, and you probably wouldn't do this. You'd probably just say, okay, this is 0, great, add 7, you're done. But I want you to notice what happens. X would equal, if I add 7, where would I add it to? I'd add it before the plus and minus. Just like here, I'd say, okay, this is 7 plus or minus 0. Now I'm going to do this on purpose so that you see we're getting the same answer twice, and we still get two solutions. We get the same solution. If I took this, and I said, all right, what this is 7 plus 0, just like we did -2 plus 1. and 7 minus 0, just like we did negative 2 minus 1 over here, we get 2 solutions. Look at it. We do have 2, right? The plus and the minus 0 gives us 2 solutions, but we're getting the same solution twice. 7 plus 0 is 7. 7 minus 0 is 7. Is because 0 is the only number you can add and subtract from a different number to get the same thing out. We get the same solution twice. That is what happens. So when you get this, this vertex on the x-axis, that's what's going to happen. You're going to get the same answer twice. It's called a double root. We'll talk about multiplicity much later, but you're basically getting the same thing out at 2 different times. This is the second case. A lot of times we get two different solutions, and saying we get 2 distinct or different x-intercepts, and we say, okay, we must be crossing there. We have to be crossing once and then coming back. If we get 2 solutions, but they're the same solution, what that's telling you, just like I showed you with the shifting, is that you have the same solution twice. You're not crossing the x-axis. Your vertex is bouncing right off of it. This we would say is one real solution. Technically, yeah, you get 2 solutions, but they're the same. So it's really just one real solution. There's no imaginary numbers here. That's it. Now, I'll make you a promise. If you just get one solution from a quadratic, it cannot be imaginary. Imaginary numbers always come in pairs. You're going to see that in just a little bit. They always come in pairs. So we can't ever get one imaginary solution. They always come in conjugate pairs, positive and negative of the imaginary part. So we've had cases where they're all parabolas, but we have 2 real x-intercepts. We've had the one, I showed that to you now because plus and minus the square root of 0 just gives you a plus and minus 0, which gives you the same number twice. And lastly, let's look at what happens when we get some imaginary numbers. So we have this parabola. It is a power 2. If I were to distribute it, don't do that. We would get this quadratic, but it's set up pretty nice for us. So when we solve for our x-intercepts or for our zeros, and we set this equal to 0, and we categorize this and say, you know what? I'm able to isolate this power 2 so that all my x's are inside of a power 2 and have a constant on the other side. I can subtract 75 to do that. That square root method is going to work nicely for us. You know, that doesn't look very nice because when we take a square root, so we looked at it, said equals 0, we said, what's the best technique? Square root method, because we can isolate the power 2 with all our x's inside of it, no x's anywhere else outside of it, nothing added, subtracted, multiplied, divided, and a constant on the right-hand side. And we take a square root. The problem is, you see it, when we take a square root, we have a square root with a negative number inside of it. You go, that's not possible. Well, yeah, it is. It's not real. It's not a real solution, but it is possible under imaginary solutions or complex numbers. We still do, like every time, that plus and minus. On the left-hand side, we're going to get this 3x minus 2. On the right-hand side, we get, well, let's think about it. Do we still have 2 solutions? That plus and minus says yes. Do we still have real solutions? That negative says no. And right now, if you're doing this and it just says, tell me how many real solutions you get, you go 0. You're done. You're done. If you start taking square roots of negative numbers, you're getting imaginaries. So you're saying, I am not going to have x-intercepts here. Realize this, people, that if you have no imaginary numbers, yes, you're crossing the x-axis twice. If you have the same solution 2 times, and you have no imaginary numbers, you're bouncing right off the x-axis. If you at any point get a negative inside of your square root, you're going to get an imaginary number and you are done as far as finding real solutions. This does not have real solutions. Therefore, if you're doing this, you go, this is not touching or crossing the x-axis at all. This is going to be floating above. How do we know above? Well, that's upward opening. There's no negative in front of that. So this is an upward opening parabola that's completely missing the x-axis. Now we have a clear picture. And that's what I want to teach you, is to understand what you are doing. Not just do it. Anybody can do this. But understanding it means that you've learned it. So when we're learning this, we're going, this right here, that's going to give me an I in there. We're about to solve it. But what we get is that that's a parabola, it's upward opening, and it's missing the x-axis completely. That's what those imaginaries tell us. So when we simplify it, We know that we could write this as -1 times 25 times 3. I'm pulling out that -1 because that -1 is what gives us the I. The square root of -1 is I. The square root of 25 is 5. And the square root of 3 is, let's leave that because it's an irrational number. So we have plus or minus 5i square root 3. And we see it right there that these are not real solutions. This is saying, okay, where do we cross the x-axis? You don't, because that I says you can't plot that on a normal number line. You don't cross it. You don't touch it, you completely miss it. When we solve this for x, do it the same way that I've been teaching you here. Add 2, but put it in front of the plus or minus, and then divide the whole thing by 3. So I'm going to do that at one step. X would equal, if we add 2, we get 2 plus or minus 5i square root 3. If we divide by 3, we get that all over 3. Now I would like to write this as two different solutions. I want to say just a couple things about it. Number one, do you still get two solutions? Yes. And we talked about how I said this a little while ago, when you have a complex solution, there will always be two of them. There will never just be one of them. Why that is, complex solutions come from taking a square root of a negative. That's right here. Whenever you take a square root of a negative, don't you always have to have a plus and a minus in front of it? Yes. So if you ever get a complex solution, it's going to have a plus and a minus in front of it. That means they always come in these pairs. There will always be two of them. If you don't have a complex solution, you couldn't have taken a square root of a negative number. And therefore, you take square root of 0, it doesn't have i's in it. But if you take a square root of a negative number and you get an I, it's always going to have a plus or minus in front of it, which always gives you two of them at a time. And we're going to find out a little bit later that complex numbers always come in what are called complex conjugates. I said that word a couple times, so I didn't define it. What a complex conjugate is same number, same complex part, same imaginary part, just a different sign in between them. That's what a complex conjugate looks like. Same stuff, different sign. Why different sign? Because of the plus and minus. Because you take that plus and minus, that's giving you this part. When you add the two, that's giving you this part. Notice you're adding the two to both of them at the same time. That's what's going on. Last couple things. Number one, you absolutely have to realize that this is two solutions. They are complex solutions, and therefore we will not be crossing the x-axis. Those are not x-intercepts. They're complex solutions, complex zeros. And lastly, I've seen this written a couple different ways. This technically is improper as far as writing complex solutions. Really, we should have 1 plus 5/2 root 3i and 1 minus 5/2 root 3i. So this whole a plus bi complex form, we really should be maintaining that, but I've seen a lot of people not do that for complex solutions like this. So it kind of depends on who you're learning this from. For me, this is fine. If you need someone, if your instructor makes you do this, as I've done it in the past, you take 2 over 2, that's 1. You take 5 root 3 over 2, and you put an I at the end. You put the I at the end of that. That's technically in complex form. So that would be the real part plus an imaginary part. I hope that makes sense. I hope that I've explained to you how the square root method works, why it does what it does, and what you're getting from it. You should be seeing the parabola. You should be in your head visualizing upward opening, visualizing crossing twice, bouncing once, and missing it completely based on the type of solution that we're getting. So I hope I've explained that very well. Next time what we'll talk about is we'll transition to factoring.